Ah yes, the battery. The unsung hero of modern everyday life, and also the bane of our existence.
What? Only 14%?
But just how does this battery work? Let's dive in and get charged up for learning about batteries and electrochemistry. Let's just start with the word electrochemistry. Hopefully that prefix makes you think of the word electron, because that's in fact what electrochemistry is all about. Where are the electrons and how can we harness their power? If you recall from way back when chemistry days, when we talked about the atom, we know that in the nucleus there are neutrons and protons, and buzzing around that nucleus are some electrons, which we denote with an E-. Now we know that these electrons aren't necessarily traveling in some orbital shape. They're buzzing about in an electron cloud all around in different orbitals, jumping back and forth in different ranges. So if these electrons are just buzzing around wherever they want to in this cloud around the nucleus, how is it that we can capture an electron and harness its power for electricity? I'm glad you asked. Notice that there are a lot of wires associated with anything that's electrical. So if we can get these electrons to travel through a wire, then essentially we can harness their power. But then how do we force the electrons to go through the wire? The short answer, we give them something they want. And what does everybody want? Everybody just wants to be happy. Then what is it that makes electrons happy per se? We can assume that an electron at a high energy level is going to be sad. And if they're at a low energy level, they would be happy. You can correlate this to the fact that if you were at a really high stress job, you would also be very unhappy. Whereas if you were sitting on a beach with your toes in the sand, you would be at a low energy level and be very happy. Now somewhere in the middle, there's also a moderate level of energy here. So maybe you're working on the beach from your laptop. You wouldn't necessarily get the full happiness of just getting to kick back and relax, but you would definitely be better off than staying at the high stress job without your toes in the sand. This is the same idea for electrons. For electrons, buzzing around a certain kind of atom would be like working at this really high stress, high energy level job. Whereas hanging out around a different atom would be like hanging out on the beach at a low energy level. And that of course would make them very happy. So the way we can get electrons to travel through that wire so we can harness their power is to give them this low energy happiness option. They would jump right on it. And hey, guess what? The battery gives them that option. But what else inside this battery makes this whole process work, where we can actually have power in the palm of our hands, quite literally? We also need something called ions for this to work. And ions come in two flavors. There's cations and there's anions. The only difference between the two is that cations form positive charges by losing electrons, and anions form negative charges by gaining electrons. For example, this outermost electron on a sodium atom gets freely donated to the chlorine atom to fulfill its outermost shell and give it an octet to be like the noble gases. When this happens, the chlorine becomes negative since it gained that extra electron, and the sodium becomes positive overall in charge because it lost the electron. And as we all know from the relationship and dating world, opposites attract. So then, this positive and negative are attracted to each other to make a neutral molecule of salt, in this case, NaCl. And all ions really just want to be neutral. That neutrality for ions is what would make them happy. So ultimately, a battery is just ions that are trying to achieve happiness and electrons that are also trying to achieve happiness. So now if we just rethink the diagram we drew before and consider the high stress environment to be metal A and the low stress on the beach to be metal B, how do we get the electrons from metal A to metal B? Well, if you were to touch the two together, you would immediately see the electrons jump from metal A to metal B, just like you would if you were at your job and you could immediately jump to the beach. You would do that. But we don't want them to do that because then we can't harness their power. Instead, we're going to give them a wire to travel along to get to metal B. And if we can cause the electrons to travel along this wire, and these electrons are going to free willingly travel along this wire, because remember, they are trying to achieve happiness. They want to be on the beach with their toes in the sand. Now this right here is literally electricity. It's electric. Boogie woogie woogie. So if we were to say put a light bulb right in the middle of this wire, you would see the light bulb turn on as the electrons pass through it. Now the thing is that electrons travel from metal A to metal B. Metal B is going to be progressively more and more negative as it gains more electrons because they're intrinsically negatively charged. And since metal A is the one losing electrons, it's going to become positive. So just like we saw with our ions before, we are now forming ions inside the battery. In order to maintain an overall charge, this battery is conducted in some kind of solution, where the cations from metal A can now travel freely through the solution and be attracted to the anions of metal B. Essentially, all of these A+ cations are going to force their way on in here and mingle with all of the anions of metal B. Once this occurs and there's no more space for any more cations to shove their way in there, we end up with a battery that is dead. Now, of course, if you're stuck with a dead battery, you have to recharge it. And when we recharge it, we're basically just forcing all of the electrons to go back to their high stress environment where they didn't want to be in the first place, and then forcing them to travel back again to their beach island once it's fully recharged. Maybe that'll make you have more sympathy for your poor phone when it dies so fast. All those poor little electrons just want to get to the beach. So inside this battery, there is a metal A and a metal B. I have a wire with a light attached to it. Let's force those electrons from one metal to the other through this wire detour and help them get to the beach, and also light up our light bulb at the same time. Ta-da! So let's analyze what we just learned. Material A was the one giving up electrons. It's the one losing electrons. So if you lose electrons, you become positively charged. And that positive charge accumulates all on metal A. Whereas material B was gaining those electrons that material A was losing. So what charge would it become? Well, if you're gaining something that's intrinsically negative, you would also become more negatively charged. And that's the charge that accumulates on material B, or metal B. So if B is negative and A is positive, would a cation, something that is positively charged, be attracted to material A or material B? Hopefully you know that opposites attract, and a cation would of course be attracted to material B, the one with the negative charge on it. For this reason, we call material B the cathode. Hence, cat for cation, because that's where all the cool cats want to go, to the cathode. How about if you were an anion, something that was fully negatively charged? Where would you want to go? Would you want to go to material A or B? Again, opposites attract, so that negative is going to be attracted to the full positive of material A. And for this reason, we call material A or metal A the anode. Just like anion, where the anion wants to go. You think you got the basics of this concept? Go ahead and pause the video now and see if you can complete the diagram, complete with electrons and the arrows for the direction where they're flowing along the wire, and a bunch of positives or negatives accumulating on either the zinc or the copper, and which way the anion and the cation in the middle will want to go. Ready? Pause now. Alright, let's check your answer and see if you were able to rationalize your way through this problem. From thinking a little backwards here, we know that the zinc was the anode, and we know that the copper was the cathode. We know that the anode is the one that loses electrons, and the cathode is the one that gains electrons. Since the cathode is gaining something that is intrinsically negative, it is, i.e. the electrons, it's going to be the one that possesses a bunch of negative charge. And since the anode is the one losing electrons, i.e. losing something that's intrinsically negative, it's going to become more positive, accumulating positive charge throughout. That means that the cations are going to want to go towards the thing that is negatively charged, so it's going to go towards the copper. And the anions are going to want to go towards the zinc, since it's positively charged. And last but not least, since we know that the cathode is becoming more negative, gaining those electrons, the electrons must be flowing in the direction towards the copper from the zinc. So we would indicate that with our lowercase e's for electron flowing along this direction of the wire, towards the copper cathode. As opposed to just using a battery, we can also analyze the flow of electrons or capture their power by creating a galvanic cell. That's where we literally have two half reactions of some metal in one that wants to lose electrons and some metal in the other that wants to gain electrons, i.e. a happy beach environment for the electrons to be at, or a really high stress environment where the electrons don't want to be. Let's check out a brief snippet of this in action. Notice that when we have these two half reactions, zinc over here and copper over here, we have it connected via something called a salt bridge. The salt bridge allows for the anions and the cations to travel from one container to the other, whereas the wire all the way up top is where the electrons are traveling from one of the metals to the other. And as the electrons move, they are always going to move from the anode to the cathode. So the direction that electrons will always flow is from anode to cathode. If we look at the zinc anode, we know that the zinc is losing electrons. Therefore, by the time this reaction is over, it's actually going to be going down in mass. It's going to be losing mass. In other words, the zinc will literally weigh less by the time this reaction is over. How about the copper electrode then? The copper electrode, the cathode, is going to be gaining electrons. And since it's gaining electrons, it's going to be also gaining negative charge, and also, which means that the cations are going to be attracted to it. That means that the mass of the copper is actually going to go up. It's going to weigh more by the time the reaction is over, or by the time the battery is dead. And of course, since the zinc is the one losing the electrons and becoming positively charged, we know that the anion SO4 - 2 would be attracted to the positive metal. So let's talk about that salt bridge. The salt bridge that connects the two half reactions. This is where our cations and our anions can flow through. Notice that these full charged species are not traveling through the wire like the electrons are. They are traveling through the salt bridge. And the salt bridge is literally what maintains the charge balance between the two half reaction species, allowing those anions and cations to flow to their respective species. The one that's becoming more negative attracts the positive ion. The one that's becoming more positive attracts the negative ion. Remember that anions will flow to the anode, and cations will flow to the cathode through the salt bridge. And again, I can't stress this enough. The salt bridge does not move electrons. It only moves the cations and the anions in solution. In chemistry, these two half reactions have a name. We call them redox reactions, and that's any time we have a transfer of electrons. As we just clearly saw, there were electrons transferring through the wire from one metal to another, and that changed their charge due to this transfer. The red part of the word redox means that it's gaining electrons or becoming negative, just like the cathode was. And the ox part of redox reaction stands for oxidation, i.e. the process of losing electrons or becoming more positive like the anode does. An easy way to remember what red does or what ox does is by the mnemonic oil rig. The word oil is short for oxidation is losing, in reference to electrons, of course. So oxidation is losing electrons, whereas rig is reduction is gaining electrons. It's important to note that whenever a chemical species gets oxidized, there's also a chemical that must get reduced. Red will always come with ox. You're not just going to have red reaction or ox reaction. You're always going to see redox reaction together. Remember, if electrons are being lost, they have to go somewhere, so they have to come in tandem. In this lesson, we talked about how batteries work, which we decided was basically just electrons and ions trying to achieve their happiness together, and us stepping in the middle of it to harness the power. Remember that cations are attracted to the cathode, and if the cations are attracted to the cathode, we know that must be a negative species, just like metal B was in our example. It's the one that accumulated negative charge, therefore something positive would want to be around it. And the reason it's gaining that negative charge is because the electrons are flowing to it. That metal B is literally the nice, beautiful sandy beach. On the flip side then, anions are attracted to the anode. They want to go to the anode through the salt bridge. And if the anions want to go there, that must mean it's a metal that is positively charged. And if it's positively charged, that means it must be losing electrons. And last but not least, anodes and cathodes are both subsets of something we call electrodes. That's basically any metal or substance where electrons can flow to or from. And then we can just kind of detour in the middle between those two electrodes and harness the power of the electron flow. Before you move on to the next video about assigning oxidation state numbers and determining whether or not a reaction is a redox reaction, make sure that you test yourself before you wreck yourself and answer these questions. Please give this video a quacks up, and when you're out of luck in chemistry, subscribe to the duck. Quack you later.
No ducks, no glory.